Hello everyone. We have here three slide sets when it comes to the Anchorage zone design. Anchorage zone design meaning the end block of the pre-stress beams. This applies here to pre-tension and post-tension beams. So the three slide sets would be labeled as 9-1, 9-2, and 9-3. As you see here, here's the end block of a pre-stress beam. On the top right hand side, what you're looking here at, this is going to be pre-tension beam, and the bottom left hand side, this is going to be post-tension beam. What happened here in a pre-tension beam, you have all the strands is going to be in place. You're going to apply the tension, anchor them, and then after that you cast the concrete on the top of the strands. The strands here is going to be 100% bonded to the surrounding concrete. After the concrete is hardened, you're going to be trimming the strands from each side of the beam, and with that you start here to transfer the force from the strands to the concrete itself. Now, the transfer of this force from the strands to the concrete is going to be happening throughout the surrounding concrete to the strand itself. Now, most of the force is going to get transferred from the beginning. It's not going to get transferred here through this side because the beginning of the force starts here. It's not going to be taking that much of a distance to transfer the force that you have in the strand to the concrete. Let's say if the depth here is going to be equal to h, most likely the transfer length is going to be roughly between 50% maybe to 60% of the depth of the concrete beam. This is here based on observation, which means this value here of 50% or 60% is going to be kind of empirical formula, empirical value that we just use in our design. Now, when it comes to post-tension beam, transfer of the force is going to be completely different because in post-tension beam, you're going to have an anchor plate at the end of the beam. Now, the strand itself is then going to be bonded to the concrete, which means entire transfer of all the force is going to happen here at the end of the beam. As if the strand does not exist and you have a point load that you have here outside of the concrete beam. This here creates concentrated zone of compressive stresses, and therefore you're going to see here tension perpendicular to it. Here's the reason. If you just assume here that you have a compression force, and then in return you're going to have another compression force here, another compression force here. Because think about this trapezoidal distribution of stress. You can split it here into two sides or two halves, the top half and the bottom half. Now take the top half here and put it as the resultant of all of the stresses to be another concentrated load coming against this applied load. Another one is going to be here at the bottom. Just assume that you're going to have here a resultant force to all the stress here above. It means that this force here is going to split into two forces. If you split into two forces, it means that definitely you're going to have some tensile stresses coming that way. So transfer of the force here is going to happen at the beginning of the block, while transfer of the force here is going to happen throughout a length that we're going to call here a transfer length for the force from the strands to the concrete beam. Having any concentrated force here in an edge or at the end of a beam, it means you're going to be developing tensile stresses perpendicular to it. As you know, if you imagine if you have a cylinder, concrete cylinder, you start to put vertical pressure on it. You start here to increase the stresses by adding more force to it. All of a sudden, you're going to see here that you're creating a vertical crack in it. This vertical crack is going to happen because the concrete wants to explode. It wants to expand laterally. So imagine here that once you put the stresses from the end, what's going to happen? You're going to see here that you're going to have longitudinal crack throughout the beam in the block. Here is the stress distribution, some comments on it, as I have it here typed and presented to you. Concentration here of the compressive stress is going to happen longitudinally at the end of the block. This is going to happen actually in both pre-tension and post-tension concrete beams. Now, in pre-tension beams, the transfer of the stresses from the strands to the beam is going to happen throughout a length. And this length here, we're going to call it transfer length. is going to be L sub T. And transfer of the stress is going to happen between the strands and between the surrounding concrete around it. In post-tension beams, we don't have this issue. We don't have this L sub T because the transfer of the force is going to happen at the beginning of the beam. I'm going to go back here for a second, just to confirm again. The strands here is not going to be bonded to the concrete, while the strands here is going to be bonded to the concrete beam. More issues here that you need to be careful about. Once you start to put compressive forces, it means that you are developing tensile forces and tensile stresses perpendicular to direction of the compressive forces. And this is given the vertical and horizontal direction. This tensile forces here, we can call it here bursting forces, and you need to resist it by providing enough reinforcing. I'm gonna go back here again to our beam. If you imagine here that you have some tensile forces, it's gonna be going up and going down. You need to resist it, and the best way, if you can provide some ties. So tie reinforcement like stirrups is gonna be a good option here, or a good solution to resist all of this spalling and bursting forces. The question is, where is the best location that you provide these ties or these stirrups at? If I understand here that the maximum stress is going to happen maybe at 1/2 of the depth to 6% of the depth, or maybe 100% of the depth, it means if I like to put here the ties or the stirrups, I'm going to put them here concentrated at the length of the end block, which is going to be equal to the depth. Which means if I have here, let's say this is going to be 2 feet, I'm going to go here to a distance of 2 feet, and for this section here of the beam, I'm going to fill it up here with the stirrups and ties. Now the question is, how can we design for this? And do you think the design for pre-tension in the block beams is going to be the same as for post-tension in the block beams? The answer is going to be no. It's going to be completely different design. In this slide set, we're going to be covering the design of the end block when it comes to reinforcing needed as ties or stirrups for the tension, and we're going to do this only for the pre-tension beams in this slide set. Now the other question is, what's going to happen here when you have here pre-tension? Is it a good idea to increase the size of the end block? Would that reduce the tensile stresses? And the answer is no. To control it, you really need to have ties or stirrups. So change the size is not going to change the amount of tensile stresses that you have in there. Here's one of the strengths. Just imagine that you apply here some compression, which means that you're asking L sub T here to be able to take all the bond stresses, because it's going to be the length over which that you transfer the force from the strain to the concrete. This is why you should expect here some cranks in this region. Also, imagine that you put here loss of pressure. What's going to happen to the concrete? Now the concrete wants to open up. As if you have a kind of a wedge that you push here throughout the concrete. Now this wants to open up and down. This is why you should expect to have here some spalling cranks. Again, the best option here and the best way to treat this is to provide vertical ties or stirrups. Also around the bar itself, if you like, you can provide here a spiral reinforcement. It's going to be very close to the strain itself. As it says here, it is essential, it is important here to provide the anchorage reinforcement in the load transfer zone. And you can do here closed ties, stirrups, or anchorage device. The anchorage device, sometimes it's going to be including some rebars around it. For post tension, it would be good if you can provide also hoops and ties very close to the face behind the bearing plate. It's going to be a little bit different from the way that you reinforce the pre-tension beams. Here's a picture. And look here at the length. The depth is equal to 40 inches, and the length of the end block is considered here to be 40 inches. And you see, right behind this plate here, you have plenty of ties. And then after this, you have some ties, but not with the same spacing as you see here. This is going to be very closely spaced. So here's the end block. Here's the center line, which is the CG location. At the beginning here, you're gonna leave a clear cover, maybe 1.5 inch. After this, you have 8 number 4 ties, and look at the spacing, 1/4 inch center to center. It's gonna be very closely spaced. After that, for the rest of the depth, the distance which is equal to the depth of the beam, you're gonna put here 13 number 3 ties. What it means here that you're gonna have number 3 ties at 2.5 inch center to center. Why do we add all of these ties? We add all of these ties to control the tensile stress and forces in the vertical direction and horizontal direction. Now imagine that you have here the pre-stress anchor is going to be right at this location. If you draw here a straight line, it's going to be almost here. Now you apply the pre-stress force right here at this point. It's going to create here some horizontal forces in this direction. Same time also some vertical forces. Both of these two sets of forces is going to be taken by this closed lines. Another picture here, it shows that most likely when you have an eye girder, once you come here to the end of it, you can make it solid. And it's going to be like a box, like a rectangle section. So in here, if you cut a section, it's going to look like an eye section, but in here, it's going to be like a rectangular section. And in this location, you're going to put the ties that you like to put here to resist the compressive forces and tensile forces due to the pre-stress injecting in Anchorage. Now in pre-tension beams, what happened that the force can get transferred through the end block throughout a length. This length here we call development length, and we are using here L sub D, which indicates here development length. It's going to be composed here of two sections. One of them is called transfer length, and the other one is going to be called flexure bond length. As you guys know, at the beginning, at the initial pre-stress, you apply P sub I, then after a certain amount of time, it's going to drop down to P sub E. P sub E is going to be the effective pre-stress force. After you apply all the pre-stress here forces, you're going to be taking this beam, and then after this, you're going to be applying the service loads. Service load means that you later on you'll apply the additional dead load, which we call here superimposed dead load, and also you're going to be applying here the life load dead. To transfer the first amount of pre-stress force that you put in there, you need the distance L sub T. For the additional forces, you need also L sub F. Total length is going to be equal to L sub T plus L sub F. We're going to see empirical equations for that. Here's a curve that shows the amount of stresses versus the distance measured from the face of end of the beam, which means the beam is going to be running this way, and actually this is going to be like the end block of the beam. At the beginning of the beam, right at the 0 point, there's not going to be any stresses in the strain. Just imagine here, if you cut a very small piece of the strain in the concrete, let's say after 1/8 of an inch, there's no stresses, there's no effect of anything. LT is going to happen first from the face of the end block to a distance, and this distance is going to be called L sub T. We have empirical formula to determine this L sub T. It's given by 1/3 FPE times dB. dB here is going to be the diameter of the strain. The additional length, which is L sub F, is going to be for the flexure bond length. This is for the applied additional load that you're going to be applying after you have this FPE. It's going to be equals to FPS minus FPE times D sub B, the diameter of the strains. Total length here, I'm going to be calling here L sub D, which is development length, which is very similar to the idea of the development length when it comes to conventional reinforced concrete design. Here's the equation again. Equation is going to be F sub PE, you divide this by 3 times dB. You have here 1,000. The reason is because this FPE that you need to use here in this equation is going to be PSI. As it says here in the equation, it says FPE equals the effective pre-stress after losses in PSI. Once you divide by here by 1,000, it's going to be in KSI. And then after that, divide here by 3, and then you multiply by the diameter of the pre-stress strain. The equation here can be simplified. I can say it's going to be equal to FPE divided by 3000 times dB. I have also another equation here for the flexure length. For the flexure length, it's going to be equal to FPS, difference between the FPS. FPS is going to be the nominal stress in the strength for the design value. You subtract here FPE, which is the effective pre-stress. You divide here by 1000 to put in KSI. And then after this, you multiply by D sub B, the diameter of the pre-stress strain. Now, L sub D, which is the development length, is going to be equal to L sub T plus L sub F. Now, here's the equation for L sub D. I'm just going to be adding here the two lengths together, which means I'm going to be adding here L sub T plus L sub F. So I can combine them in one equation. Now, this L sub D is going to be the minimum length required for the pre-stress strains. It's going to be the minimum development length that you can provide it there for the strains. Now, how to design the ties and the stirrups at the end of the block for pre-stress, for pre-tension beams? We have here this empirical equation. Empirical equation meaning that someone came here, he built lots of specimens for pre-stress in the block beams. And what he has done here, he applied certain amount of force at the end of it. And he was able here to measure the amount of tensile stresses. He came up with this equation here on the top. It says here that the force in the stirrups is going to be like vertical force. It's going to be equal to nearly 1% of PI, the initial pre-stress, times H divided by L sub T. My understanding that L sub T is going to be nearly 1/2 to maybe 6% of H. This is my understanding. Which means in the back of my mind, I'm going to see here H divided by L sub T is going to be almost equals to 2. So this factor here is nearly about 2. Now 2 times 1% times PI, which means I'm going to have a force here, which is roughly about 2% P sub I. That's my understanding. This is to start with. Now, if you like here to average the stress, you're going to be going here to maybe 50% of this value. How is that? Now, the same force here, you need to take it by the stirrups and the ties that you provide in the vertical direction. Meaning, this force is going to be equal to the cross-section area of the ties when you cut a section, like the horizontal section through the beam. And let's say that you have one tie with 2 legs. A sub T is going to be equal to 2 times the area of 1 rebar of this tie, multiplied by F sub S. How much is this F sub S? Let's say here, F sub S, to control the amount of crack that happened in the block, is going to be taken as 20 KSI. I understand that the yield strength for the steel is going to be maybe 6 KSI, but I'm going to be limiting the stresses to 20 KSI just to control the amount of cracks that you're going to see here at the end of the block. Again, to make an average for the stresses, I'm going to be taking maybe 1/2 of this 20 KSI. Therefore, the A sub T is going to be equal to the following. It says here is going to be nearly 2% PI H over Fs divided by LT. How do we came up with this equation? I'm going to say simply, let's set this equation is going to be equal to that equation. This force here is going to be 10% PI H over L. This equation here says the force is going to be also equals to A for the stirrups times Fs, apply here by 0.5. Set this equal to that. What's going to happen? You can come up with this. You can come up with this equation here. Now, I want you to notice here that H over L is about 2. Therefore, this force here is going to be nearly about 4%, which means the cross-section area of the ties is going to be equal to 4% of the amount of pre-stress force that you apply in the front of the beam divided by 20 KSI. So a simple way of doing it is just to take 4% of the pre-stress force and divide this by F sub S, which is 20 KSI. I have an example on the pre-tension and block beam design. It says here, design the anchorage reinforcing needed to prevent spalling cracks. They give me here P sub I. P sub I, the amount of force given in pounds is going to be 376 and 110 pounds. The stress here, the effective stress, is going to be 154,980 psi. You have here half-inch strands, so the diameter for the strand is going to be half an inch. Now let's see how can I figure out the length first. Transfer length. Transfer length is going to be based on PI. We have here an example for the design of pre-tension anchorage zone for beams. And our task here is to determine the amount of ties or strands and stirrups to be added at the end of the block. Initial pre-stress was given at 376, 110 pounds. FPE, effective pre-stress, is going to be 154,980 psi. Diameter of each strand is going to be half an inch. I have this equation here for the transfer length, which is based on F sub PE. As you see here at the bottom, you say FPE divided by 3,000 times dB. You note here that I don't really need to find out L sub D. It's going to be just L sub T, which is a transfer length, because this is what I have in this equation to determine the amount of ties. In this equation here, if you take FPE divided by 3,000 to put it in KSI, and then you multiply here by 1/2, which is the diameter of the bar, is going to be 25.83 inches, which is roughly about 1/2 of H. Now I understand why I was saying 1/2, because most likely you're going to have maybe 24 inches, 25 inches, and most likely the depth of a pre-stress beam is going to be maybe 40 inches, 50 inches, so forth. This is going to be the range I'm looking at. The cross-section area of all the ties needed is going to be equal to 2%, multiplied by PI, divided by F sub S, H over L sub T. Now here's my equation. It's going to be 2%. 2% amount of pre-stress force is 376, 110 pounds, multiplied by the depth, divided by L sub T, the 25.83. You divide this by 20,000 psi, which is F sub S. Again, this F sub S, we're going to be limiting it here to 20 psi, just to control the amount of cracks. Needed cross-section area, A sub T, based on this equation, says here 0.61 square inches. I decide here to use number 3 ties. It's going to be a closed tie, and the closed tie is going to have 2 legs. One cross-section area for number 3 is going to be 0.11 square inches. When you have here 2 legs, it means for each stirrup, you're going to have 0.22 square inches. Now look at the needed. I have here 0.61. For one tie, closed tie, I'm going to have here 0.22. Meaning that I need here to have 2.78, which means at least I'm going to have here 3 stirrups. 3 closed ties here to resist the amount of tension that you have here at the end of the block. As it says here, it says use number 3 ties. In reality, I cannot just use number 3. Maybe I'm going to provide here number 3 at 6-inch center to center, meaning that I may end up with maybe 6 to 7 stirrups in this location. Now let's see here what AASHTO or Caltrans method. This is going to be based on the BDS, the Bridge Design Specifications or Practice. One of the latest editions that we have there, which is on June 2018, is about the anchorage zone design. It says here, based on AASHTO, the PR is going to be the required, the fact of bursting resisting of the pre-tension anchorage zone by transverse reinforcement, which means this is going to be the demand that you apply here to the end block zone is going to be equal to F sub S times the total cross-section area provided. F sub S, as it says here, should not exceed 20 psi. Okay, so I'm going to say here, let me use here Fs is going to be equal to 20 psi. And As is going to be the amount of vertical reinforcement that you provide in the stirrups and in the tires. It says here PR should not be taken less than 4%. It's going to be very similar to the equation that we were just talking about in the previous section. What I did, I said this is going to be about 4%, probably. So here in AASHTO and Caltrans, they say just take it 4%, which is the minimum value that you need to consider. This here can be used for pre-tension anchorage zone, and they put it here again. It is repeated in the section 8616. As it says here, PR is going to be equal to Fs times As. Fs is going to be taken as 20 psi. And PR is going to be taking 4% of P sub I. Now, this is going to be very simple when it comes to design. And I'm expecting that you guys in your project that you should be able to design the pre-tension anchorage zone. And this is going to be very specific to the double T members that we have, and also the beams, if you like to do it for the beams. We have one example. In this example here, we have 16.6 inch strength. The grade is going to be 270 psi. When you have here number 6.6 inches, and you have 16 of them, you're going to have a total of 3.42 square inches. The amount of initial force, which is a jacking force, P sub I, is going to be equal to 75% of the 270 psi. Multiply this by the total cross-section area of the strengths. And with that, you have 703 kips. So great. Now I have this PI. Now the amount of force needed here to be resisted by the ties or by the strands is going to be 4% of that force. This force here I just determined to be 703 kips. If you take here 4% of it, you're going to end up with 28 kips. Meaning that now I have 28 kips applied vertically and needs to be resisted by stirrups. Amount of area required, total cross-section area, if you cut a section through the beam, is going to be equal to that force divided by 20 psi. This 20 psi, it comes from the fact that it says here, the stress in the steel should not exceed 20 psi. We go back here to our example. Now you can see here, I'm going to be using here number 5. Number 5, it has cross-section area of 0.31 square inches. When you have here 2 vertical legs, because you may have here closed tie or maybe an open tie with 9-degree standard hooks at each end. So each one of the stirrups is going to have a cross-section area of 2 times 0.31 square inches. With that, you're going to have 0.62 square inches. Now take the 1.41 divided by 0.62 square inches. With that, you're going to end up with 2.3. There's a typo here from the reference book. I used it. It says here it's going to be 1.31. This should have been only 0.31 times 2. And look at this. I mean, the mistake is very obvious. If you take 1.41, divide this by 2, divide by 1.31, you should end up by a number which is going to be less than 1. It's just a typo because number 5 rebar, it has a cross-section area of 0.31 square inches. You should see here as 0.31 times 2 because you have here 2 legs. Now I know that I need here 3 stirrups. It's going to be number 5, and each one of them is going to have here 2 legs. You need to provide this ties or these legs. It's going to be within 1/4 of the height. the section height. Meaning, you'd better place this in the first quarter from the left-hand side. Left-hand side, which means beginning of the end block of the beam. In this picture here, it shows that you're going to provide here number 5 stirrups. As I said, it's going to either close stirrup or I can have here 9-degree hook. The reason that we have this 9-degree hook, to be sure that's going to be anchored, because most likely you're going to see here a rebar and here's going to be a rebar. And once you anchor it, you're going to be gaining the tensile force that you wanted or resistance throughout this stirrup. If you don't have here any anchorage, you cannot have here any resistance for the spine. With that, we're done with this slide set, and thank you very much.